research areas. So my primary area is in human-robot trust for my dissertation work, where I'm looking at how we can properly calibrate trust with robots. So you guys have probably seen videos where people hop in the back seat of a theoretically autonomous car, or a car with driver assist, or something like a Tesla or one of the other ones, and just sort of take a nap while it goes through traffic for them and trust it, and then get into accidents. This is a phenomenon we're trying to study and figure out how to help people make better choices in the situation. So how to help them understand what these robots and autonomous systems are truly capable of. So we're looking at the overtrust aspects of that. We're looking at what we call trust calibration. So how does the robot express to a human how much you should trust it, how much faith you should put in it going forward, what it's actually capable of in a way that people accept and understand. The teaming aspect, we have a cool project right now that I don't have great graphics for yet. We're just coming into the lab testing on it, where we're going to be doing search and rescue with robots. So teams of humans and robots searching an area to look for victims or hazards. And we're trying to measure how they trust each other over time. So when the robot makes a couple of mistakes, as is inevitably going to happen, how does the humans' trust in it change over time, and how can we affect that? And then, of course, I'm working on field robotics as well, like these marine robots where they're moving outside in the real world. They have to interact with humans doing normal human things who've never been trained to work with a robot. There's bystanders, there's other people just doing their daily work out on the water or on the roads or wherever. The robots have to be able to work with them in some way. And we've been doing a lot of this on the perception side of things. So this is an image of one of the robots at MIT moving along a buoy field. So you've got a bunch of different power boats over here that are just anchored. And it's able to detect them, say that they're boats, and put little bounding boxes around them on the radar so that it can see where they are going forward and identify what this thing is compared to this image. But I want to talk to you guys about my class today, because this, I think, goes a little bit more towards the sort of service aspect you guys are working on, trying to teach graduate students and senior, junior level undergrads how to do robotics. So they've learned, theoretically at least, how to be engineers, how to do some basic programming and electronics. How can we teach them to do robotics research? So when I started at UMass Lowell in fall 2019, I was talking to some of the other robotics faculty, and they were mentioning that we're starting to get some critical mass here. At the time, I think I was the 5th robotics faculty hired. Now we're up to, I think, 7 or 8, something like that, and hoping to expand that every year. So we're starting to get some critical mass here, but when we have graduate students joining us to try to do their master's or PhD, oftentimes they don't know all of the tools necessary to be good at robotics right away. And so it's time to give them a class to just sort of standardize that. On top of that, we're in the Boston area. We've got so many different robotics companies up here. I pass Boston Dynamics on the way to Costco. I pass iRobot on the way to work. Like, they're all over up here. This is really something that the students could use to get a good job in the area. So this is by nature, because it's going to be introducing them to all of robotics, it's a little bit more about breadth over depth. We're not going to teach them how to make walking robots. We have another class for that. Not going to teach them how to make marine robots. We're going to teach them generally about robotics. And I should say, this is the slide that I give students at the beginning of class to give them an idea of what we're doing here. So I wanted to show you guys what I present to them. So we're teaching a robot middleware here. It's called ROS. You don't have to worry about that. But basically, it's a bit of software that sits between what you would write to make a robot do something cool and the hardware on the robot. So it's the thing that enables us to write cool stuff on the robot. So you don't have to write something to control an arm or control a motor or anything like that. You're writing a higher level something to make the autonomy side work. And then, of course, I wanted to reinforce all the math that they learned in undergrad that they probably forgot about and didn't think was important at the time. But as a engineer in the world now, I can tell you it definitely is important, and I should have paid more attention back then, so I'm sure they should have too. So there's a basic idea of a somewhat humorous drawing of what teaching in this class. So you've got the real world out here, and we've got a robot over here, and the robot's made up of some sensors to see the world around it, made up of what we call actuators, or to the motors and the arms and stuff like that that do things in the world. And in between, you've got math. And it's a little bit of a joke there, like there's more to it than just math. But basically, you've got all this math that they learned at undergrad that they probably don't remember anymore. And don't worry, I'm not going to go into the math today. This is really high level, just to explain generally what we're going over, but this is the point of the course. This is what I give them as the philosophy going in. So the idea of this is experiential learning. We have twice a week lectures for 75 minutes, I think. My lecture is I aim to take up about 30 to 60 minutes of that 75 minutes. The remaining of the time, we have a robot teaching lab that I'll show a picture of in a minute, where they can do work, or over COVID times, I'll talk about how we did that. But the idea here is to learn by doing. So not just me lecturing on chalkboard, not just me putting up slides and people falling asleep in class, but actually let them get their feet wet with this and get some work done. During COVID times, I would tell them the class would be via Zoom and recorded in case they can't make it. Regardless, I've been posting my slides on a publicly available website so that they can be useful to other people and so that students can refer back to them at any time. Makes it a little bit easier. They're not behind some university page. And then, of course, I tell them at the end here that this is a senior grad level course. This is exactly the text I give them at the end of exactly what I'm going to tell them next week. It's going to require a lot of work. This surprises students. Some of them, for some reason, think it would all be just fun and not work. But they also come in from a variety of different backgrounds. Some of them are master's students who've been out in the working world for 10 years, haven't taken a class in that long. And so they've forgotten how to take classes. They've forgotten that homework exists. They've forgotten all these things. They don't remember necessarily they're going to have to learn a lot of this on their own, that I will give them pointers. I'll put them in the right direction. I'll show them slides about how things work. But the actual last step of them going from me explaining it to them and them doing it, they're going to have to plug away at and get to work. And they're going to have to actually debug the robots, which we'll talk about more in a minute. So a lot of this is made possible by what's called the Duckytown Foundation. Duckytown Foundation was a group that started out of MIT just before I got there, actually, I think 2016-ish. They taught a class where a bunch of the postdocs and grad students got together. So we should really have a class on how to teach about these autonomous cars that are coming out and help the other grad students and undergrads get to know how to make these sorts of autonomous cars. So they made this little robot here, which I have one right here as well. So you can get a sense for scale. It's not all that big, maybe about 8 inches long, but it's got 2 wheels and a camera, and that's pretty much it. 2 wheels, a camera, and a little computer called a Raspberry Pi on board. So it's a very simple platform. It's relatively inexpensive. They sell them to us for about $200 right now. It was a little bit more expensive when they were prototyping it, as happens when they when you're buying new things. But regardless, they've been making this little platform for about 5 years now. Just made a new version actually. And to go with the little platform, they have what's called the Duckytown. So this is an area where you can set up these individual tiles. The tiles are just exercise mats. You can find it at pretty much any store these days, any Walmart, Target, anything like that. They've got these sorts of exercise mats. You can get them on Amazon for maybe $15 for 4 or for 6 of them. And just plain white tape and yellow tape to make lanes. So you can put these together in all sorts of different configurations. You can make a little town. You can make just a little circular track. Do what you want. But the idea then is the students will take this robot here and program it to stay between the white and yellow lines, just like a car would, and drive around, stop at the stop signs, turn at the intersections, and make it through this area. And this is somewhat challenging for students who haven't done robotics before. Frankly, it can be a little bit challenging for students who have, because a lot of this depends on, say, the lighting in the room. You know, this camera is a fairly simple, inexpensive camera. It can't see all that well. So the lighting in the room, the slickness of the tiles, the different tiles have different sort of slicknesses, so the tires can slip just a little bit. But it's a challenging problem, but a good little platform to do that. So what does this look like during a semester then? During a semester, this was taken right before we went virtual for COVID. Actually, we had no idea that was coming, but the students had just gotten their robots. I had 25 or so students that semester, and this is, you know, maybe about 15 of them in the lab, in the robot teaching lab here, where we've got some really nice computers set up that have the software they need on it. They were able to get together. You can see a couple of them working together. You can see people working on hardware, people getting the software ready, all different stages of it here. And it's a really collaborative environment where you can just reach out and, you know, ask your friend, hey, this doesn't look right. How does yours look? And compare notes and so on. So this is what it looks like when we're in person. This is the sort of thing you might expect from that. But of course, that didn't happen. So I'm going to step back just a little bit here and talk a little bit about what a robot is in terms of what we're trying to teach in the class. This is the diagram I gave you in the beginning. You know, you have some sort of real world here and a robot over here. I'm going to make a simpler version of that. So ultimately, we've got a robot that's moving around in the real world, and we've got the world that's moving around it. And the robot affects the world some. It either moves around in it and bumps things, or it has an arm and picks things up and moves it. And the environment affects the robot because it's going to change in ways that the robot might not have expected. So this is a loop, a little feedback loop here, where the robot has to be constantly paying attention to the environment, and the environment is constantly changing depending on what the robot's doing or whatever other things in it are doing. We can really split this up into things that are totally beyond our control and things that we can control. So we can't control the environment in general. The robot can move things around in it to some extent, but if you're driving on the highway, you have very limited control over what other people do on the highway, right? So you can't actually make them do anything in particular. You just have to react to them. But then we have the things we can control, or in engineering terms, the things we can design. So these are the things we put into the robots. That would be the what type of camera we put on the front of the robot here, what type of wheels we use, the software that goes in the computer, and so on. So there's all sorts of things here that we can actually design on the system. And that's what we focus on in this class, how to design these things such that we can do the environment. We can further break down the robot part of this, the things we can design into a couple of different chunks. So the robot needs to be able to see the world around it, and it needs to be able to do stuff in the world. But in order to do stuff based on what you've seen, you need to think about it. If you're driving on the road, you see the traffic around you, you see the lines on the road, you see any construction barrels or anything else going on, you maybe see your GPS tell you to go a different direction. You then have to think about how to turn that into how much you turn the wheel, how much you push the gas and brake pedals, and so on. So this is something that we do every day without even consciously thinking about it. But it's the basic loop that you can consider here, that we're constantly observing the world, thinking about what to do in it, and then doing the things that we want to do or something close to that. So we need to put this on robots. We tend to call this the sensor side and the actuator side. This thing in the middle here is generally called autonomy. And that's what my class really focuses on, is how to build up this thinking component. And this could look something like this, which is a little bit more complicated, although they get much, much more complicated than this even. But you have some sensors in the world. You need to be able to detect what's around you, the things you shouldn't hit in the world, so obstacle detection. So all the barrels and the road markings, the other cars, those sorts of things. You need to be able to map them in some way. So you need to be able to say that, okay, the sensor detected it, but how far is it actually from my car? I can see it in camera image, but how do I map that from the camera image to a distance away from me? Or if I see it in the camera image and I see it from, maybe most cars have LiDAR or radar these days. So how do I combine those two things into one coherent map of the world? You need what we call state estimation, which is estimating, calculating where you are in the world. GPS makes this relatively easy at the few meter resolution, but often we need even better than that. So this is taking in all various sensor data and integrating it to decide where you are in the world, how fast you're moving in it, where any appendages are for a humanoid robot, and so on. And then you need to do some sort of a high level plan. So you need to be able to say, I'm here at 11 a.m. I'm supposed to be in Lowell for a meeting. So how do I get from here to there? What's the plan to get from here to there? And then further, what's the plan to get from my driveway to the end of the street where I make my turn, and so on, each step of the way. And at some point that becomes what we call controls. And controls is how much gas and what angle of the steering wheel should I be at right now? Like, what are the actual inputs I'm giving to the car to get from point A to point B at any given moment? And so this is generally the sorts of things we talk about in the class. We actually cover each of these things a little bit in my class. So we often think about robots then as systems of systems. So you have all these subsystems in it, like the camera by itself is a full system that somebody makes that may never go on a robot. It may be a webcam like I'm presenting on you here, it may be something else. But for the robot, it's just one component. And as added difficulty here, we can't really stop paying attention to the world to think about what we're doing, right? If we stop paying attention to the world to plan our route between here and Los Angeles or something really far away, then we won't be able to react in time if a car cuts us off on the way. So We need to sort of see while thinking while doing. All these things need to happen at the same time. And they tend to use a layered approach in a modern system where you have, like I said, this controller at the end that's the actual thing that tells the gas and the brake what to do, that tells the robot arm where to move, which servos to turn at which times, and so on here. And we have this sort of like I showed you there that, we take in the sensors, we figure out where we want to go, we plan how to get there. This is the preferred path of how we do it. We also generally have a path between the sensors and any planners. We have a path for if an emergency happens. So if something gets in your way and say, let's have the sensors connect directly up to something else that's running in parallel to all of this. And then a couple of ways that a human can stop the robot should anything go wrong. So this is a more general approach. We actually don't end up looking at the emergency stops as much in this class because these robots are small and don't particularly need them. But it gets at why it's very important for engineers to know how to debug things, especially in robotics. So as an engineer, I think a lot of people would think it was great if I did know all the answers out of the box, but I'm generally not expected to know the answers immediately as things come up. So instead, I'm expected to be able to figure out what can or did go wrong and then fix it so it doesn't happen or doesn't happen again, as the case may be. So I don't necessarily need to know everything that could possibly happen, but I need to be able to figure out what could happen in a system when I'm designing it, or figure out what did happen when we're working on redesigning a system. So this means debugging skills are critical, and in my opinion, can only be taught with hands-on learning. So this little image here is from, at least ostensibly, the first actual bug as an insect that caused a problem in a computer system. It was a moth that got caught in a vacuum tube in, I think, the 50s on a older computer. And oddly enough, the word debugging was actually used already. Bugs in the system was actually used already as a term before this happened. But still, you have to know where to find that moth got caught in the system. You have to know where to find what went wrong and figure out what happened. So we have this fairly simple rollout platform where you might say this isn't too many moving parts to work with, and that's intentional. We don't want to give them too many moving parts while we're teaching them. But basically, there's a single camera, there's 2 motors on it, there's 1 computing system on it, and there's a fair amount of software that comes with it. But even with this, to be able to narrow down which part is going wrong, whether it's a piece of hardware that's broken or a piece of software that's malfunctioning, or more likely, where the student didn't really understand what they were asking the robot to do and what the rest of the pieces did as they were moving around, it's actually possible. This is still a challenge for them to narrow these things down on the DuckyBot, despite it being a simple platform, simple-ish platform, and still worth them doing, and I think a good platform for them doing experimenting on. Okay, so the class is, as I said, experiential. Each student ends up with their own little DuckyBots to play with in class. They can either purchase them directly from duckytown.org. We got a discount, so they're down to $200 for that. So within the scope of the price of a somewhat expensive textbook, they can purchase them used from past students, just like a textbook. You can just buy a used system like that, or you can borrow them from UMass Lowell. And I should point out that they don't get to play with these arms. This is a UR5 arm in the Nerve Center we have on campus, but it was a good example of hands-on robotics. So I thought I would put it up there. So each student builds their own robot, or if they bought it used or borrowed it from us, they have to figure out how well the robot actually works and test or repair it such that they can make it work properly. So each student has their own robot. They're responsible for making it work in the first lab. They program the robot in a computing language called Python so that they can make their robot work and accomplish the labs we give them. And the labs go like this. So in their first lab, they assemble the robots, and if they're working from home, the tiles, they can experiment with it. In-person times, we usually do this in the teaching lab over here. The second lab, a couple weeks later, they make the robot move for the first time. So I tell them to just make it move for 1 meter straight, make it move in a 1 meter circle and a 1 meter square. This is to give them some experience making the robot actually move around in the world without being too critical about them. It doesn't matter too much if it goes in a perfectly straight line or not. Third lab is to calculate based on how much the software told the wheels to move, how far the robot was supposed to move in that time. So not the human measuring it, but have the actual robots make that calculation. Fourth lab is to use the camera to find the lane markings on the sides of the road here. And fifth lab is to make this a whole loop in a fully autonomous system to control the robot to stay within these lanes. And this is getting modified a little bit as we go on. Every time I teach the class, it'll be the fifth time this semester. Every time I teach the class, things get changed a little bit. That's the basic idea. So we can essentially build up a system one piece at a time so that they can learn how to make robotics. Okay, so as everybody's well aware, back in March, we were suddenly told that students aren't going to return from spring break and must attend class from home. So suddenly things got very interesting for us. In this very hands-on class, we had to figure out how to do virtual, which is the big takeaway I wanted to give you guys today. So we had some enabling technologies here that allowed us to do this. We had, of course, Zoom, which you're familiar with. I'm talking to you through it now. And this program called Slack, which you may not be familiar with, but it's popular in the engineering world for messaging. It's a way that you can have sort of a big message board workspace for your group, and it has multiple channels. So I set it up such that one of the channels is, help with my robot hardware. One of the channels help with some of the software, and so on through it. And then students can post messages. They can directly message each other. They can directly message me. I would discourage that as much as possible. They can post files, images, and videos, and so on. As it turns out, I use Slack for research, so I'm already on it much more than is probably healthy. So I'm there to answer questions whenever they might have it. They can post problems at any time, and either I or another student will see it and help them. So if they post publicly, other students are very good about helping them with actually answering their question and figure out what to do. So this became critical as we went to virtual. It was used some before we went virtual, but it was used all the time afterwards. So basically the first class we had through Zoom, I discussed with the students and said that, you're each gonna have to figure out how to run the robot in your own home. And this is probably gonna be challenging, but we don't have any other options right now. Especially at that time, everything was chaos, as I'm sure you remember, so we really didn't have any other options. So basically provided materials so they could build their own Ducky Towns at home, or loaned them equipment if they weren't able to get it. So we used some university funds to directly purchase this equipment from Amazon. So it's just, like I said, exercise mats and tape. Didn't order on Amazon, delivered it directly to the students, never got touched by anybody else. So it was as safe as we could possibly make it at the time. And we set up group and one-on-one debugging sessions over Zoom. So just like we're doing here, if you can imagine this, except so, periodically students are holding up their robot and asking me, well, this part came off, how do I fix that, so on. Or point the camera at what the robot's doing on the ground right now and ask me, why is it doing that? And we figure out what happened there. And they did this with each other all the time. A couple of them were able to meet in person in small groups to figure some of this stuff out. One critical feature I didn't know existed before this is that when someone screen shares, like I'm doing with you right now, you can actually request to take over control of the application that's being screen shared. So you can request to take over PowerPoint from here. I have to approve it, but you can still request that, which means that if they present me with their computer to say that I'm getting this really weird error and I don't know how to solve it in the lab, I'd sit down with them and maybe ask to take a look at their laptop and type on it and figure out what's going on. Through Zoom, I can actually do that as well, which was very useful for us to figure out. And of course, this required extra flexibility with deadlines. When hardware goes wrong, it takes a lot longer to replace it than just grabbing another part in the lab and moving on with your day. My time became much more limited, so it was hard to be able to find the time to get with them and so on. And then at the end of the semester, we set up a time for students to drop off all the borrowed equipment one at a time, so they'd be as safe as possible. And we carried that through the last couple semesters as well. So if you recall, this is what things look like when we're in person. We have this wonderful lab space. We have a Ducky Town set up, and we have some support to actually set these things up and tear them down and so on. Well, what did this turn into in COVID times? This is what my setup looked like. Wanted to post mine, so I wasn't posting into the students' home environment. But basically, I had this DuckyBot here and cat Oscar, who you got to see earlier. So this is what it looks like to test a robot during COVID times. You'll be driving the robot around. This is under autonomous control. I was trying to tune it so it didn't swivel quite as much. And of course, Oscar helped out by just being a big roadblock in the way. So this is the sort of thing that you're dealing with now, and the extra work that it took to get past that. Let's see, so just for a couple of numbers here, the first time I taught this class was fall 2019. I had 23 students or so. It was a once a week class. We usually teach our grad classes once a week in the evenings, and went to the robot teaching lab every class for between 30 and 60 minutes. We handled debugging problems in person. So if someone had a problem, I had them come to my office hours or after class, and we looked at it. In spring, just before COVID, I had 25 students. We transitioned to a twice a week class to make my workload a little bit easier. And plan to spend maybe about half to 2/3 of the class period in lecture and the rest spent in the teaching lab doing hands-on debugging with them. Post-pandemic, that meant that suddenly we had to, or I had to start recording some lectures beforehand, especially early on. We had a summary in class, and then we would just have them ask questions and debug things in class, hopefully in front of the rest of the students, so we can get some of that lab atmosphere to learn from as needed. Once we went fully virtual, I changed things a little bit up again. So the last couple semesters, you'll see this is basically the same, except the number of students. My students doubled in the fall of 2020, and actually we're set for another big semester. When I checked this morning, I had 42 sign up for my class starting next week. So another big semester here, and this was entirely over Zoom. So we set up times or ways to mail robots to students or have them pick them up on campus if they live locally. Gave lecture over Zoom live, but recorded it so that the people who couldn't make it could join. As you can imagine, some students had to take time off during the semester because they caught COVID or were taking care of someone who caught COVID, or because their work schedule suddenly changed because their work was swapping between virtual and in person and so on. So try to be as flexible as possible with that, and was available over Slack as much as possible. Last semester, not quite as many students, fall always seems to be a little bit bigger, but the rest of this is pretty much the same. Now, this is going to be a little bit more of the trend here. And so this is what I wanted to leave on, that there's these things called massively online open courses coming out that you might or might not have heard about. But basically, this is an attempt to teach people bite-sized things that they want to know in their own home. So the Duckytown Foundation is currently creating a bunch of courses. They just delivered their first one. They built a new robot for this that has, it's a little bit more expensive, it has a little bit more hardware on it. But basically the idea between most of these, they call them MOOCs for massively online open course, is that the course is free to take if you just want to take it, but costs money if you want to get some sort of a credit for it. So if you want to get graded assignments and a certificate at the end that says you took the course, then you need to pay the money. So this particular one is $50 to get the credit, and also requires purchasing a robot so you can actually do the experiments in your own home. And that is about $400 with all the equipment to go with it, all the tiles and tape and signs and so on. But the idea is that robot will be used over multiple classes that are being developed right now. Now, I'm not officially part of this with the Duckytown Foundation. I might teach one of their courses at some point, but haven't figured that out yet. But this was happening before the pandemic. But during the pandemic, of course, the technology has really gotten in place to make this a lot easier and to help people essentially build up the skills they need to be able to take this sort of course online. So they're putting together a lot of different courses in this, and this is one of the futures for teaching. I know our university is moving more to online classes as much as possible in order to make things easier for non-traditional students who maybe want to get a master's or a PhD while they're working full time. And generally make things easier and more flexible so that more people can get the degrees and certificates that they want. So anyways, I think that, yep, that's all I have there. So thank you guys very much for having me here, and I'm happy to take any questions.
Paul, I'd like to ask a question about $50 for credit. Is that college credit, or is that
no? So this is through something called edX, which is what runs their system. So some colleges will accept a certain sequence of these courses for credit, but the $50 is for usually a short course. So this would be, if you wanted to get college credit for this, it might be a credit hour or something like that. But I'm not aware of any colleges that currently take the Duckytown course for credit at the university, but it is possible to do some of the other MOOCs for credit.
The $50 is inexpensive for an online course.
Yep.
Even if you throw the $350 into the robot. Okay. Okay, thank you.
Yeah. Yeah, the idea is that potentially thousands of people can take this course at once, and it doesn't cost them any more per person except grading, most of which can be automated. So, yeah.
And Paul, on the online course, Kentucky Town Foundation, do they have an instructor there with you the whole time, or is it just everything you're doing is just pre-recorded?
Yeah, so the MOOCs do them a couple different ways. They all have pre-recorded components so that students can sort of stop the lecture and go back and forward as they want to for their own learning. This particular one was a synchronous course, so they did have students were expected to turn assignments in on a certain time. They would hold office hours to help students with problems. They have a good support infrastructure online as well. Some of them are completely asynchronous and you may never actually meet the instructor. In fact, some of our online courses, even at traditional university, are that way, where the instructor posts all the material and makes themselves available for certain office hours, but everything else is the student can message me when they have a problem. I can message them when I'm back in the office to help them with it, and back and forth. So basically the answer is both ways are possible, and it often depends on what either the instructor or the class feels is necessary.
Paul, what's your opinion of online learning versus in-person learning?
Sure. It highly depends on the class. So for my particular class, online learning was okay. And I think it's something that the Duckytown folks have been able to do a good job with as well. I didn't have quite as many resources as them, especially during COVID while we were creating stuff on the fly. So I think that in person will be a little bit better for this sort of hands-on robotics course for most students. But some of my students did amazingly well with the online component. So some of my students really did come together and decide, I'm going to build up this whole environment at home, and then I can work on it whenever I want to. I'm not tied to the lab. I'm not tied to coming to class at a particular time, and really thrived there. Other students really need that personal interaction. So I think the future is that we're going to have to offer things both ways. And hopefully it's not me offering things both ways in the same semester, because that's twice as much work. But universities as a whole are probably going to have to offer things both ways, such that they're able to give students the environment that the individual student needs to succeed going forward.
Paul, can you do me a favor? Is Oscar with?
Yes.
You get to them, that they can see Oscar. Oscar, explain just, he is how old?
He's 12 now, 13. He turns 13 this month.
Very, very helpful.
Yes, he's very helpful. He joins me for most of my meetings, and usually says hi.
Anything else?
Any other questions?
Did you record this?
I did. I got 90% of it. I forgot to start it, but I got most of it. So all of the robot stuff is all recorded, and I'll have it up like we usually do. Paul, can you do me a favor? Would you mind your slide deck to me that I can attach?
Wait a minute.
Sure.
Can you do that? I mean, is it?
Yeah, not a problem.
Okay, and I'll attach that with the, I'll put a link to that too.
Paul, thank you. I remember seeing you when you first started out in robotics.
Yep.
Yeah.
Yep. You guys were very helpful to us then.
That was awesome.
It was over my head then, too.
They can probably count bills.
Oh, yeah.
You've given me all kinds of ideas. We have a resort of the Lake of the Ozarks, 40 acres back on the coast, and we have rebuilt each building, added roofs and things. It's just like it was original, like 100 years ago. Thank you.
Thank you, Paul.
Thanks for having me.
Thank you.
I'll talk to you later. Have fun.
Bye. Okay, for the good of the club, I guess, just to formally announce our board meeting, we normally have it the first Tuesday of the month in September. Due to conflict for a couple of us, me included, we're pushing it back to the second Tuesday of the month, so it's.
Now, we do have, supposed to have club assembly on Wednesday the 7th. If you want to do that time, I will not be here. I'm actually working. I will try it, see what happens this year. I'm not holding my breath. But we'll see what happens. So I won't be here. Yeah, well, that goes through. I'm done. There's a bunch of subs that will be done at that point. If his lawsuit goes through, but anyway. So I don't know if you still want to do that, or if somebody wants to come up with a program. I won't be here, which means this won't be set up. Just letting you know up front, unless you are gonna be here and can bring all that.
I can do it the way I was doing it.
Yeah.
iPad phone.
Paul, what precipitated him changing from MIT to you?
He, I'll stop recording, hang on. Well, Bill's still on, never mind, I didn't see that. Paul, first of all, when Paul was at Georgia Tech, he had an opportunity to go to MIT. And he said, no way, I am not putting up with the damn New England winters, end of discussion. He was at at Georgia Tech, and a buddy of his had already been up to MIT. And they were going up for his wedding. Paul was the guy's best man. And was going up to the wedding, and the guy said, well, make sure you bring good clothes. Well, yeah, I'm gonna be at your wedding. He said, no, I got an interview for you. You're probably gonna be hired at MIT. They made him an offer he couldn't refuse, and up they moved. By the way, they shipped their furniture, but they drove from Atlanta to Boston with 5 cats in the car. Now, at each rest stop, we would have been down 1 cat, I guarantee. But anyway, they did. MIT was great. The only issue with MIT was it was all grants-based. So if the grants dried up, his job went away. He had this opportunity at Lowell. He said, I don't know if I'm going to get it or not. It'll work. It's teaching and grants, so it would be guaranteed income regardless. But what they were really looking for, they were one requirement, or not requirement, but what they were really looking for was they wanted somebody who could liaison with MIT to where the 2 universities could work together. When they found out Paul was at MIT, they said, yep, this will work. And he's been there a few years and has done some with both of them. So that's the reason why he left MIT. It was strictly grants-based. And
He wasn't teaching that much.
he was not teaching at all. It was all grants-based, and you couldn't do much during the winter. When he showed the pictures, they were on the Charles River. They started on the Charles River in March, and they finished up in November, and it is cold up there. That water is rather chilly. They were wearing wetsuits, everything else being out on the river. It was not a lot of fun in that respect. What they're doing was a ball of fun. And we went out with him on one of them when we went up to visit. The labs that you saw are the labs that he works in. Those are the labs at UMass. The building is an old, cinder block building, been around forever. And they literally, for most of the engineering building, they tore out the walls. They left obviously the load bearing, but they tore everything else out. Those are their test beds. Those are their sandboxes. They call it a sandbox because kids play in the sandbox. These aren't, well, some have sand in it because of the texture, but this is where they set the stuff up to test it. And then
Are they
obviously
funded by a lot of robotics companies?
they're funded by some of it. UMass is a state school, so a lot of it is state supported.
But the Ducky Foundation?
Ducky Foundation has donated some of it. If I recall correctly, that is donated to a degree. They've reduced the price to the universities.
But someone's funding the foundation.
Someone's funding all of that, yes, and I don't know who that is. But he showed us this a while back, actually, when we went up there, because Duckytown was, they were doing it in person, and he showed us this whole layout. So it is quite interesting to see. And rightly so, we are very proud of it. And we're proud of both kids, don't get me wrong. But we're proud of him with doing all of this that he definitely didn't get it from me. The engineering mind is not mine. So.
Yeah, we know.
Yeah, I know. And I still have trouble with that I will be teaching it Tuesday and Wednesday and the following Thursday in September. So, yeah, we're gonna-
Well, it's kind of interesting. Part of our trip, we took it at the Ford, we took a tour of the Ford factory. You know, and of course, you're watching it. We watched them put the windshield in, the F-150.
Yeah.
All robotic, you know, and it is one of the many things. I mean, fascinating.
it's really neat to see how far, I think Andy and I were talking about it. You know, they show, you see all the flubs, but if you go back to the early days with the rockets, where you're trying to get a rocket off the ground and it went up, 2 feet, and then just collapsed on itself, or it went up and they had to hit it, as he put it, the remote kill switch, so it wouldn't fall down range, all of this stuff. It's amazing just in the lifetime, and I'm not sure if I have, and I do when I haven't seen him for a while, but Jim Ginzel is the one who got Paul started on computers. He would bring over a bunch of crap computers that almost didn't work and said, here, Paul, play with them. And Paul would take them apart and put it back together again. This was at Northeast Middle and at North. And he was just, he knew that's what he wanted to do. That's where his mind works. And it's great. So I still blame Jim for all the crappy, old, will never be used again computers. They're still sitting in our basement.
Maybe they're antiques now.
Well, we do have a Commodore 64 down there.
Yeah.
And I showed my dad one time what a floppy disk really is. The 5.5-inch floppy.
Can't buy one now, can you?
Nope. No,
Weren't they?
yeah, the original one's right there. Yeah, and then they came down to a 5.5 square. Then they came down to the 3 1/4, the hard shells. And God help you if you had 30 discs that you were loading Office on or something, and you were missing disc 28. It just stopped. You wouldn't load anything else down.
Kind of interesting, that little 3.5-inch disc. We sold Emerson Electric all those supplies that gave them department and everything.
Yeah.
That's what we built them with, the 3.5-inch diskette. They could have it all charged back.
Yep.
And today it's even much more expensive there than that.
My original VIC 20. That order. Floppy disk. Program on there.
We had Mary's first computer that they actually, this work from home thing is new. No, it wasn't when Liz was born. So 1988, Mary worked from home on San Diego. Or I guess it was still Monsanto at that time. Might have been Solution, but gave her a literally big box computer. The second weighed about 75 pounds. And here's all the information, the phone that you shoved in the receiver for the internet connection and so on. That was a 286 processor, but it had what was called a 386 emulator. It had a little chip in it that made the 286 think it was the next level up, so it could work better. And this thing has more power in it than that computer ever had.
Speaking of computers, Apple II manual signed by Steve Jobs sold for $787,484. Apple II manual signed by Steve Jobs.
Wow.
You probably got a gold mine in your basement.
Yeah.
Otherwise, a bunch of junk.
I'm leaning more towards the second than the first.
Anybody else have anything for the good of the club?
Did I win the drawing today?
No.
Except the drawings in the back